There's something incredibly strange happening to our universe right now, literally as we speak. Welcome to this Curious Orbit Explainer. Today, we're going to explore a cosmic mystery that has completely upended our understanding of reality. For a really long time, we thought we had the grand story of the cosmos pretty much figured out. You know, a clear beginning, a middle, and a totally predictable end. But it turns out the universe is behaving in a way that absolutely no one expected. It's this cinematic, almost unbelievable reality. There is an unseen, unfelt force out there, in the dark, and it is actively altering the very fabric of space and time. So, you might be wondering, what exactly is tearing the universe apart? Well, to understand just how wild this is, we have to look back at what we thought we knew. For decades, astronomers observed that distant galaxies are generally moving away from us. The farther away a galaxy is, the faster it appears to be receding. We knew the universe was expanding. That was a foundational pillar of modern cosmology. But in the late 1990s, scientists discovered something that changed the entire story forever. The universe isn't just expanding, its expansion is actually accelerating. Something is literally stepping on the cosmic gas pedal, pushing the universe apart faster and faster every single day.
Now, to really wrap our heads around how strange this is, we have to visualize this expansion correctly. It's really easy to picture a giant explosion, kind of like a firework, with galaxies flying outward through empty space from some central point. But actually, scratch that, that's completely wrong. Instead, I want you to imagine the universe like the surface of an expanding balloon. As you blow air into the balloon, the rubber stretches, right? If you were to draw little dots on that balloon to represent galaxies, those dots wouldn't actually be moving across the rubber itself is stretching, carrying the dots farther apart. That's what's happening to our universe. Space itself is expanding. The galaxies are just along for the ride.
Okay, let's dive into this a bit deeper. The scientists who figured this out didn't just take a wild guess. They had help from a very specific type of dying star known as a type Ia supernova. These are extremely bright stellar explosions, but more importantly, they explode with a very consistent, predictable level of brightness. Because astronomers know exactly how inherently bright these explosions are, they can look at how dim they appear from Earth and calculate exactly how far away they are. They essentially act like cosmic distance markers, or, mile markers on a dark highway. By studying these distant supernovae in the late 1990s, two independent teams of astronomers managed to map out the entire expansion history of the universe.
And what they found was an absolute shock to the scientific community, like jaw-dropping. You see, everyone expected the expansion of the universe to be slowing down. Why? Well, because of gravity. The universe is full of matter. Stars, planets, gas clouds, black holes, and all that matter has mass. Gravity pulls things together. It's kind of the ultimate cosmic brake pedal. So over billions of years, the collective gravitational pull of all the matter in the universe should have been acting like brakes on the cosmic expansion, gradually slowing it down. But the supernova told a completely different story. The brakes just weren't working. In fact, gravity was losing the battle entirely. The expansion was accelerating.
So what on Earth, or rather, what in the cosmos, is overpowering the gravitational pull of the entire universe? Scientists gave this mysterious phenomenon a name: dark energy. But here is the uncomfortable truth. We still don't know exactly what it is. It's really important to understand that dark energy is not a literal black cloud of smoke. It's not some dark physical fluid you can just scoop up and put inside a laboratory container. It's completely invisible. We only know it's there because we can see its profound effect on the cosmos. We infer its existence because we literally observe space being pushed apart. It is the ultimate cosmic prime suspect, and its true physical nature remains one of the greatest mysteries in all of science.
If you aren't thoroughly astounded yet, consider our cosmic energy budget. Everything you have ever known, touched, or seen, every star in the night sky, every planet, every comet, your house, your own body, is made of ordinary matter. And yet, that ordinary matter makes up only an incredibly tiny 5% of the universe. Dark matter makes up another chunk. But dark energy? Dark energy dominates the universe, accounting for roughly 70% of the total cosmic energy budget. Think about that for a second. The vast majority of our universe is made of something we cannot see, cannot touch, and do not fundamentally understand.
Now, what's really interesting about this slide is the clear distinction it makes, because it's a super common point of confusion. We hear dark matter and dark energy and naturally assume they're just two versions of the exact same thing, but they are entirely different cosmic beasts. Dark matter acts like an invisible anchor. It contributes extra gravity, helping to pull galaxies and massive large-scale structures together so they don't just fly apart as they spin. Dark energy, on the other hand, is the exact opposite. It's associated with pushing space apart and accelerating the expansion of the universe. One pulls structures together, the other stretches the very fabric of space apart.
So how do we even begin to explain what dark energy might actually be? Well, one of the leading ideas is surprisingly simple, and it goes all the way back to Albert Einstein. It's called the cosmological constant. In this mind-bending theoretical picture, empty space isn't actually empty. It's not just a blank void. Instead, space itself has its own intrinsic energy, which is often called vacuum energy. According to this idea, as the universe expands and creates more space, it also creates more of this vacuum energy. Because this energy remains a fundamental property of space itself, it exerts a constant outward pressure, producing that accelerated expansion we observe today.
But, as elegant as that sounds, there is a massive, head-scratching theoretical problem. When scientists use quantum physics to predict how much vacuum energy should exist in empty space, the math produces a specific number. But when astronomers look at the actual cosmos and measure the dark energy causing the acceleration, they get a completely different number. And I mean completely different. The simplest theoretical estimate isn't just slightly off, it is wildly, spectacularly wrong, off by a staggering factor of 10 to the 120th power. That's a 1 followed by 120 zeros. It is literally described by some as the worst prediction in the history of physics. This massive mismatch is known as the enormous quantum discrepancy, and fixing it is currently one of the deepest unresolved problems in all of theoretical physics.
Since we obviously can't put dark energy in a jar, we have to hunt the invisible indirectly, piecing together its cosmic fingerprints. We do this by tracking distances with those supernovae we talked about earlier. But we also look for frozen sound waves from the early universe, known as baryon acoustic oscillations, which essentially act like a giant cosmic ruler for measuring unimaginably vast distances. We study the pristine snapshot of the Big Bang's leftover radiation, the cosmic microwave background, which gives us the universe's earliest baby picture. And we conduct massive galaxy surveys, mapping millions of galaxies to see exactly how matter is distributed across enormous volumes of space. By combining all these indirect clues, scientists are acting as cosmic detectives, reverse engineering the invisible forces at play.
When we combine all these clues, the universe's evolution looks like an epic cosmic tug-of-war. 13.8 billion years ago, the universe was incredibly dense. Matter and gravity completely dominated the expansion history, pulling in and actively slowing down the expansion of space. But as the universe kept expanding, billions of years later, matter became more and more spread out. Its density dropped. But remember the cosmological constant? If dark energy is an intrinsic property of space, its density stays exactly the same even as space expands. So, as matter thinned out, dark energy's influence remained steady, until, finally, it took over. In the present day, dark energy is definitely winning the tug-of-war, driving the acceleration we see all around us today. So, the crucial point is, what is the ultimate fate of the universe? If dark energy is currently winning this cosmic tug-of-war, where does this all end? The discovery of dark energy didn't just change our understanding of the universe's past. It completely rewrote the possibilities for its ultimate future. Let's look at the main scenarios scientists are currently exploring.
The most widely accepted scenario under our current models is known as the heat death of the universe. If dark energy behaves like a true cosmological constant, its density will remain perfectly constant forever. This means the universe will just continue expanding faster and faster for all of eternity. Over enormous timescales, distant galaxies will be pushed so far away that their light will literally never reach us. They'll just fade from view entirely. Eventually, gas clouds will drift too far apart to ever form new stars. The last stars will burn out, and the cosmos will just go quiet. The universe will become infinitely large, but it will be colder, darker, and incredibly dilute. Basically, a vast, freezing emptiness.
But what if dark energy isn't constant? What if its pushing force actually gets stronger and stronger over time? This leads us to a much more violent theoretical model known as the Big Rip. In this extreme scenario, the accelerated expansion eventually becomes so immensely powerful that it overwhelms all other forces in nature. It would literally tear apart gravitationally bound clusters of galaxies. Then it would tear apart individual galaxies, stripping away stars. Eventually, it would overcome the gravity holding solar systems together, flinging planets into the void, and in its final moments, it would tear apart the very atoms that make up reality. Now, I want to be super clear here so we don't cause any existential panic. This is a highly hypothetical model. The Big Rip is for sure not a confirmed prediction of standard cosmology. It's simply one theoretical outcome if dark energy behaves in a very specific, highly aggressive way.
Now, you might be wondering about the opposite extreme. Could the universe eventually hit a limit, stop expanding, reverse course, and collapse back in on itself? In older cosmological models, before the late 90s, this scenario, called the Big Crunch, was considered a really serious possibility. But because we now have hard observational evidence of accelerated expansion, gravity simply doesn't have the strength to pull it all back together. Because dark energy is driving the bus, a simple future Big Crunch is no longer the expectation under our standard cosmological models.
To truly know our fate, we have to answer one critical question. Could dark energy change over time? Right now, some of the most enormous, sophisticated astronomical surveys in human history are actively mapping billions of galaxies to measure the precise expansion history of the universe. They desperately want to know if dark energy's strength fluctuates, because if the data reveals that dark energy does change over cosmic time, then Einstein's cosmological constant is wrong. And if it's wrong, our entire understanding of fundamental physics, gravity, and the laws of nature will require a massive, ground-up revision.
And that really brings us to why this matters so profoundly. Dark energy isn't just some abstract math problem about galaxies billions of light years away. It's telling us something incredibly fundamental about the reality we live in. Imagine that empty space isn't actually empty. Imagine that everywhere you go, between stars, between planets, between the very atoms in the air around you right now, the vacuum itself has physical properties carrying a force that dictates the evolution of the entire cosmos. The biggest mystery in physics isn't necessarily a massive object or a black hole. It's hiding right there in the seemingly empty space between the galaxies. Dark energy challenges our most basic assumptions about what nothing actually means.
The universe is laying out the evidence for us piece by piece, but the final answer is still hiding out there in the dark. So I want to leave you with a question to ponder. If scientists discover that dark energy isn't a property of empty space, but a completely new kind of physics, what do you think they'll discover? Tell us your theory in the comments and subscribe to Curious Orbit.